get started. It's my pleasure today to introduce Professor Tirthankar Dasgupta, who's been my colleague in the statistics department since 2008, I think. And he's one of the world's leading experts in experimental design, which is an incredibly important topic for data scientists, especially in this age of A/B testing and randomization and experiments, which has a long history in statistics, but then is also has a lot of modern applications throughout data science. And he has many years of working both on the theory and the practice. He spent years working in India as a data scientist, although it wasn't called that at the time, and actually doing experiments before he went to grad school, and he realized to go deeper into it, then have to study more statistics, and then it's been doing a lot of great work on that. So he kindly agreed to introduce us to this topic today. So let's all welcome Tirthankar. Thanks.
Let me. Thanks, Joe. Can you all hear me? Can you hear me at the back? Okay. Great. So, well, first of all, my sincere thanks to Joe and for giving me this opportunity to interact with you. Data science is incredibly important these days, and it was important earlier. I mean, there are plenty of concepts which have been transmitted from different worlds into the modern world of data science. And I believe one of the important aspects which data scientists should care about is experimental design. The name may seem to be a little weird to people who have not been exposed to the topic earlier. So experiments are done by many people, including people in the physics and chemistry labs, by engineers, by social scientists. But particularly, I think what we refer to as experiments here is specifically an art of collecting data which will help you make better decisions about causal effects of different factors. Now, you might be wondering at this stage that most of this data science class is probably kind of about looking at data and analyzing it and finding efficient algorithms to identify patterns, right? So is collection really important? So I would argue that collection is indeed very important, and you might have a lot of data, but still you might want to think carefully about what your real questions were and how this data was collected and how to sample from that data. And of course, when it comes to new studies, it's obviously a very important aspect to think about that collection and to link it with the type of analysis which you are eventually going to make. So let me start with a very simple question, and many of you would be probably familiar with this kind of a question because you're all emerging data scientists. So let me pretend that I'm the CEO of a pharmaceutical company who's coming up with a new brand of aspirin because after this 1.5 hours lecture, you all have a little bit of a headache. So you might want to have an aspirin to make sure that that headache goes away within 1 hour or so. So I'm trying to figure out with some data whether that's really the case or not. And I want to advertise accordingly. So I have some data. So this is my question to all potential data scientists. And if you can help me with this, probably I'll offer you a nice, lucrative job in my company. So I have some data, and I had actually studied the case of 100 people who had headaches, and they took an aspirin each. And 90 of them were cured in an hour, right? So I consider that as a very strong evidence that my brand of aspirin does cure headaches. What do you think? So would you be able to support my view with some nice graphs or maybe some p-values or some statistical tools which can help me take my case to FDA, and probably I won't be sued by people if I put forward an argument, an advertisement. So what do you think? Is there anything missing here? So you're not convinced? Yes, Chris?
Yeah, so we don't know what would have happened if those people would not have taken the aspirin.
That's a great point. Any other concerns? Well, of course, this is a data science class, right? And you might be wondering that this is too small a data, 100 people, right? Okay, and of course, I mean, Chris has brought up a very valid concern. But before that, suppose I amp up my kind of data collection, and so I have 10 million people now, and who had headaches, and they all took my aspirin. I have that on record, right? And so basically, 9 million actually were cured after an hour, and that's a fact, right? So this is, of course, bigger data, right, and substantially big data, right? Does this suggest that aspirin relieves headache within an hour, right? So probably not, right? Because already Chris brought up a very valid point that, well, we don't really know what would have happened if these 10 million people did not take an aspirin, right? So whether this disappearance of headache is a manifestation of taking aspirin or not is not evident from this fact, right? So there's a question which cannot precisely be answered with just this piece of information, right? So we need some more information. But even other than that, I mean, we might want to think, like when I'm asking this question, does this suggest aspirin relieves headache within an hour? Is my question really well formulated? Whom am I talking about? Am I talking about 100 people, 1 million people? Where are those people from, right? Am I talking about people from Harvard, people from Japan, people from Africa? So what is the scope of my inference, right? So this is really not a well-formulated question. So basically, we have some missing aspects here, as he pointed out. So first of all, we don't have any information about what would have happened to these 100 people or 1 million people if they did nothing, right? So for example, they could have drank plenty of water. They could have drunk plenty of water, or simply relaxed for an hour, took a power nap or so, and that possibly could have cured the headache, right? So that part of the information is missing here, right? So however, so what that means is if I actually had something, so now I would strengthen kind of my database, and I would say that, okay, now I also have 100 people who actually did nothing. They had headaches, but they did nothing, right? So I call the aspirin-taking people as the ones who are exposed to the treatment. So that's something which is kind of the treatment here. And I also need a control group, right, to compare them, who did nothing, right? And then I find that out of 100 people, 80 were cured within an hour and 20 were not, right? So there is still a difference, right? So what would be my conclusion here? So if you're not sure, let me create one more situation, right? So suppose 90 were cured after taking aspirin and 10 were not. And the people who did not take an aspirin, about 50% were cured, right? So that obviously gives us stronger information, right, in terms of certain kind of uncertainty aspects, which is kind of related to our decisions about making causal inference. So probably you might say that, well, this seems to be a little stronger evidence as compared to the previous case, where we had almost a similar distribution, right? How about this one, right? This seems to be a much stronger evidence, right? That now the proportion of people who are cured by taking an aspirin and people who are cured without doing nothing, by doing nothing, is substantially different, right? So you might actually think that there is some effect of aspirin, but these questions need to be quantified, right, and asked more carefully, right? So at this point of time, how many of you think that this would help me kind of market my product, and this would be a good enough evidence to create an advertisement which would say that taking aspirin makes a substantial difference? Yes? How many of you think that this is not enough? Okay. So, and the rest of you are not going to make a comment. Okay, that's fine. Well, that's fine. So, at this point of time, let me look at my next slide and add some more information here. So let's assume now that I didn't tell you before, but the 100 individuals who were exposed to treatment or who took an aspirin, they actually were these nice young ladies out here. And the people who did not take an aspirin, and out of them 90% said that they were not cured, they actually were these old gentlemen, right? So what would you say now, right? So perhaps here you can realize that there is a confounding effect going on, right? I don't know really whether that difference which I was looking at, right, was really due to the fact that the aspirin cured the headache, or was it an effect which was created by the characteristics of the subjects in my experiment, right? Because they were vastly different, right? So now comes the question of when I'm really kind of thinking about a treatment group and a control group, in order to make a valid comparison, they need to be similar in some respect, right? But that again is not a very well-defined statement, right? What do I mean by similar, right? So I have to define what similarity means, and how do I guarantee such similarity? So if I'm conducting a study now, what are the ways in which I can guarantee that this treatment group and the control group are similar in some respects, right? So this is one of the important stages. So some of the important points which I think would be clear is, first of all, whenever we kind of analyze data to try and answer a causal question, we should try to define our objective in a much more precise manner. Like, for example, we should formulate the question in a more of a data science language, right? What I was formulating right now is not precisely in that language, right? We should identify the scope of inference, like whose headache are we talking about? This class, all people of Harvard, people of Cambridge, all people of United States, right? So we need a treatment group and a control group, because implicitly there is a comparison, right, between people who have taken the treatment and people who are not, right? And if I could have observed the same outcome on the same individual, that would have been great, because that would have been my causal effect, right? But the fact is, one part of that information will always be missing, right? Those who took the treatment will not get the control, and those who did not take the treatment, right, obviously that part is missing, right? So I need a treatment and a control group, and they need to resemble each other in some way or the other. So these groups should be identical. But how do we define this identical aspect, right? And how to achieve that kind of identical groups? So one of the issues which we'll see is going to come up is one of the challenges which is being posed by this increasing amount of data is now when I'm looking at these 100 individuals, now I have hundreds and thousands of pieces of information in terms of covariates with respect to their medical characteristics, right? And then when I'm talking about balance, I really have to think about how I can match kind of these two people, right, taking into consideration these covariates, and how should I link or relate my analysis to the way in which I do this selection, right? So that's one of the key things which we are going to discuss today. When we analyze the outcomes, these outcomes should be consistent with the way in which we make our selection. They should be related to and consistent with the design. And by design, I mean, what do I do to learn about my question, right? So in what way do I do this assignment? In what way do I divide this population of units I'm studying to treatment and control? And of course, by analysis, we want to calculate a measure which will tell me like how strong my conclusions are, right? So clearly, as you can say, if these two groups were identical and I was looking at this 90-10, 10-90 type of distribution, implicitly, the conclusion would be strong, right? And in statistical language, that strength can be interpreted in different ways. Like we can talk about testing of hypothesis, we can talk about p-values, right? So these are some of the things which we would like to talk about, but they have to be related to and consistent with the way in which you kind of collect your data, right? So that's something which we are going to discuss with different examples today. Okay. Any questions so far? Okay. So before I move on, let me kind of give you some examples about some modern day experiments which I have been associated with, and many of these actually are taking place in and around Harvard. For example, experiments in education. Schools in New York are trying to come up with new initiatives, like whether it makes a difference to kind of introduce a bonus scheme for the teachers, right? So that's a new initiative. They have several different kinds of new things like a quality audit coming up, right? Whether it would be meaningful to conduct something like a quality audit in the middle of the year, whether that would improve. So they are trying to test different types of new interventions and try to find out whether these would create a causal impact and improve the performance of the schools. So that's an example. Marketing, when you look at these consumer products today, you all use dishwashing liquids, right? So do you know kind of how much of effort goes into identifying like which product or which brand is going to be marketed the next? So these consumer companies, what they do is they come up with a large number of test products, right? And then they identify a huge set of households. And then they randomly send these 10 or 11 test products out to these households, right? And then they try to gather a survey to figure out like which of these, whether it really makes a difference or whether they can find out one which will be really prospective, right, in terms of being marketable to this set of households. So that's the kind of marketing experiments they do. You have the Melton lab at Harvard. They try to convert these stem cells to insulin-generating kind of beta cells in the pancreas because they can provide you with a treatment to diabetes, type 2 diabetes. And they try to treat these stem cells with different chemical modulators. And there can be 25 to 30 of these modulators. So each is like a switch, right? So you would like to figure out like what is the optimal combination, like switching on or off these 30 modulators that is going to help maximize the chances of converting these stem cells into insulin-generating beta cells, right? So nanotechnology, law, internet, A/B testing, all of you are familiar with situations where you log on to a website and then you find a new ad popping on one corner, right? And so that's, many of the time, that's basically a manifestation, that's a situation where the website is trying to come up with a new intervention and try to judge your reaction to that, right, in terms of a new ad. So that's A/B testing. And A/B testing basically is very similar. The basic framework is very similar to this treatment or control type of scenario where you're exposed to two or more different situations. And we are trying to assess your causal effect. So these are some examples, right? So it's very interesting that the way in which we can actually handle these different kind of experiments from a vast multitude of fields is very firmly grounded in theory, which actually took its birth several years ago, right? And of course, as is true for all disciplines, we need to make changes, we need to modify our theory depending on the criticality or complexity of the things that are coming up these days. But there are certain elements of this theory which are so powerful and so interesting that they are still very, very relevant in the modern era, right? So that's what I'm going to argue and try to give you an account of. So this theory actually, a lot of it was developed in the early 20th century. And Sir R.A. Fisher, I believe Joe has already introduced you to Sir R.A. Fisher, who's one of the fathers of modern statistics. He was hired by this agricultural group of people at Rothamsted experimental station in the UK. This is how these plots look like. So you can see there are these plots of land where they would test the effect of different kinds of fertilizers and different kinds of irrigation methods with the objective of enhancing the yield of crops, right? So he actually published his first book on design of experiments in 1935, and it was based on a whole bunch of experiments which were conducted in this Rothamsted experimental station, right? So how is that still relevant, and what are some of these key ideas? Let's take a look at some of these key ideas. But before that, I think one thing which I implicitly must have introduced to you when I talked about this aspirin example is we are thinking about an individual, right? So who could have been exposed to either of two situations, right? Taking an aspirin or not. So implicitly, there are two potential outcomes, right, of this experiment, out of which one would be observed and the other would be missing. If you knew the two, your causal inference would be straightforward, right? But the interesting fact is one is missing, right? So this idea of potential outcomes, right? Now this actually was originated by Jerzy Neyman. So these two, if you are asked, like, who were the two most influential personalities who really developed this kind of entire theory and applications of statistics in the 20th century. So the first two names which come to mind are Neyman and Fisher. And unfortunately, they had a very bitter rivalry towards C in the middle of the century. And Fisher was a man of a very strong opinion. So they started hating each other after a bitter fight at the Royal Statistical Society while Neyman was presenting a paper. So Neyman, in his 1923 paper, formally originated this concept of potential outcomes. So we'll come to that in a minute. Although R.A. Fisher never formally acknowledged this idea, but he implicitly did, which is evident from one of his statements made in 1918 when he said, let's read this carefully. See, he says, if we say this boy is tall because he has been well fed, that means you are trying to make a cause-effect relationship, right? We are suggesting that he might quite probably have been worse fed, right? And that, in this case, he would have been shorter, right? So we are visualizing two possible outcomes corresponding to a good diet and a bad diet, right? Out of which you're observing one and trying to make a statement on that, right? So there's something which is missing, right? So let us look at a specific example, and then we'll expand this to various different kinds of situations. So the type of experiments which Fisher started kind of working on. So we are just trying to make some inference about the effect of a new fertilizer on the yield of tomatoes, right? And let's say we have 11 agricultural plots here, right? And we have an old fertilizer, we have a new fertilizer, and we are going to use either of them on each of these 11 plots and figure out whether they make a difference with respect to the yield. So we visualize two potential outcomes here corresponding to this plot of land, right? Number one. So if this plot received fertilizer A, it would have a potential outcome and a potential outcome. So T represents the treatment, which is a new fertilizer here. C represents a control, which is the old fertilizer here, right? So then I would have these potential outcomes for each of these 11 plots, right? And for each of these units, I can visualize a unit level effect, just like what would have happened to me if I took aspirin and if I didn't, right? So that's a unit level effect, right, which I could define. But of course, I cannot estimate any of these unit level effects because of the simple reason that I'm going to observe only one of these, right? So what kind of summaries might I be interested in? So I might be interested in these averages, right? And it's possible for us to estimate these averages, right? So this is something which is a function of all these potential outcomes, some of which will be observed and some of which will be missing, right? But I might be interested in something like this, right? But I may be interested in something else also. I may be interested, for example, if these individual effects are very skewed, they are not symmetric, right? I might also be interested in the median of these unit level effects, right? So why traditionally people didn't study the median is because the mathematics is a little complicated, because the average is a linear function, right? So it's easy to do maths, right? And that's why most of the mathematical theory in the era when we couldn't compute, right, were based on linear approximations and linear functions, right? But that's no longer a restriction. So that's an advantage which we have standing in this kind of 2015 today, that we can do a lot of things which even Fisher, I mean, obviously could not imagine, right? And we'll see what some of these exciting things are. So now, this is the data which you observe, right? So the question is, how do we now generate this data, right? So one more interesting point which I would like to mention at this stage is this idea of potential outcomes is based on one very fundamental philosophy, right? That philosophy is try to separate what you want to estimate or what you want to study from what you do to achieve that level of knowledge, right? So this potential outcomes is like the universe, right, about which you want to make an inference. So the advantage of potential outcomes is the moment I create that universe, it is clear to me what my scope of inference is, right? And now I am, as a data scientist, I'm generating the pieces of information from that universe by a technique which only data scientists would use, right? And that technique is the art of randomization, right? So why do I use randomization? We'll come back to the discussion a little later. But one thing you probably would realize at this point, that my task is to assign maybe six of these to the new fertilizer and 5 of these to the old fertilizer. I would like to probably assign one more to the new. But you could come up with a different way of doing that assignment as well. For example, you could toss a coin, right? And you could decide which fertilizer is going to be applied to which plot of land. But then I may run into a potential trouble, right? That trouble is after 11 coin tosses, each of which result in tails, I might end up getting all my lands assigned to the new fertilizer, right? In that case, I may not have any data, right? So I'm just thinking about doing this in a randomized manner, so I define an assignment variable, binary variable. 0 represents its assignment to the old one, and 1 would represent its assignment to the new one. So let's do this assignment, right? 0 old, and then some ones and 1 zeros, right? So I have these data. So as you clearly see, now I can visualize. This is something which a data scientist has at hand, right? Now I'm trying to go back one level and trying to think, like, how did this come, right? So they were generated from this universe of potential outcomes through a mechanism which I devised, right? And that's called randomization. So how did I generate this randomization, this vector of zeros and ones? So I prefixed, right? Let's say 5 would be assigned to old and 6 would be assigned to new, right? And then I kind of think about all possible ways in which that can be done, and then I choose one from that. That's just a one-line code in any kind of standard programming language like R, right? So you could generate this with equal probabilities. And now I'm looking at these two observed averages, and I'm looking at the difference, right? And that difference is something which should give me a logical answer kind of to this question, whether there is a difference between these two groups. But how to connect that better to this potential outcomes? Now let's see that. So now let me define a hypothesis, right? And so this hypothesis, in statistics, we define a null hypothesis, which is sort of the status quo, and we try to test that null hypothesis using some techniques, right, which as a data scientist you would be able to apply and figure out whether that hypothesis is valid or there is enough evidence in support or against that hypothesis, right? So I call this hypothesis a sharp null hypothesis because this hypothesis is no effect of fertilizer on any of these plots, right? So it's a sharp null hypothesis. And how to assess this hypothesis? So this is a very beautiful way in which we would go about testing this hypothesis. It's called a stochastic proof by contradiction. Most of you would be familiar with proof by contradiction, right? So how do you do that? So how do you prove a theorem by contradiction? You state the theorem, right? And then you assume, right, it to be true, right? Or assume it to be false, right? And then you show that there is a contradiction, right? And then you say that hence proved. So that is something which we are going to do. We are going to assume that this hypothesis is true, and then we are going to see what are the effects of the hypothesis being true and match it with what we actually observe, right? So let's see what we are going to do, and I'm going to take you through these steps very soon. So first we are going to calculate the observed value of a test statistic. So whenever in data science you perform a hypothesis test, right, you have a test statistic, which is a function of the data which you observe, right? And the test statistic can have different values based on different realizations of the data, okay? So I calculate that value of the test statistic, and then I assume that the hypothesis is true, right? And then, and then I impute these missing potential outcomes, right? So everything is based on that picture, right? That frame of potential outcomes. So if I'm thinking about a hypothesis and that hypothesis leads to filling those gaps, right? That would be the imputation of missing potential outcomes, right? Then how do you test a statistical hypothesis? You have this test statistic. You calculate its value, right? And then you find out its distribution under the null hypothesis. That is, if the null hypothesis were true, then what would have been the potential realizations of the test statistic, right? I get that distribution, and then I see whether what I have observed is really kind of matching with that distribution. Is it very unusual, or whether that's kind of very common with respect to that distribution, right? That's basically the art of testing a hypothesis, right? So we determine if the observed value is unusual, right? So let's go through these steps in this particular example. So I'm looking at this data, right? So the step 1 is to calculate the observed value of the test statistic. And the test statistic, I could define the test statistic as the difference of these two averages. Now, I could do something else also, right? For example, I probably could have divided these by their respective standard deviations and taken the difference. That's also possible, right? So there could be different choices, but at least the test statistic should be meaningful in the sense that it is really measuring what you are eventually trying to measure, right? So there is a relationship, and you understand that this difference is kind of related to that difference of the averages of the potential outcomes in some sense, right? So I calculate the test statistic from this data. And so I calculate that absolute value because the sign is not important. What I really care about is the difference, right? So now I want to test whether this value is unusual if the null hypothesis is true, or is this quite natural if the hypothesis is true, right? So how do I do that? Now I will generate repeated values of this test statistic, right, under different randomizations, okay? So what do I do? So now I impute the missing potential outcomes under the null hypothesis. So remember what my null hypothesis is, right? Null hypothesis is no effect of fertilizer on any of these plots, right? So that means whatever I observed with the old fertilizer has to be exactly the same as what I should observe with the new fertilizer, right? So that's the imputation. So similarly, I would fill in all the missing potential outcomes with exactly what I observed, right? Correct? So now my table is complete. And this is true if and only if the null hypothesis is true, right? So now let's generate a different assignment from this, right? Now, when I generate this new assignment, it should be done exactly the same in the way in which I did the original assignment, right? So I have to use that same mechanism for generating 6 ones and 5 zeros the way I did it originally, right? So that's how I relate my analysis to the way in which I generated the data, right? So this is 1. I observe the new one, 0. I observe the old one, right? And I generate a new assignment mechanism exactly the same way in which I did while my original data were generated, right? And then I calculate a value of this test statistic, right? So that's my new value of the test statistic, right? And I can do that. I can keep on doing that. I generate one more, right? So this could be a possible assignment where the first 5 are zeros and then the last 6 are ones, right? And then I could again calculate the test statistic. It's 2.82, right? And then I could have another assignment where the first 6 are ones, the last 5 are zeros, and I could calculate it again. And I could calculate this again and again and again, right? So then, this is the total possible number of values which the test statistic might have. And why is this? Because the way in which I randomized is basically choosing 6 out of 11, right? And this is the total number of combinations, right? Which in which this assignment can be done, right? So for each of this, I actually can compute one value of the test statistic, right? And then I can put them in the form of a very common representation which you are all familiar with. That's a histogram, right? So that's the distribution of the test statistic. It looks interesting, doesn't it? It looks like kind of half of the bell-shaped normal distribution, right? And the reason is we took the absolute effect, right? We just kind of took the positive part of it. If we didn't, it would have looked like the complete bell curve. Like, isn't that fascinating, right? We didn't invoke any of the standard statistical assumptions of any normal distribution or anything like that, right? We just did randomization, and then this distribution looks like something which is kind of very similar to a model, right? So there is a very interesting connection to mathematics. So you can actually prove that when you do it this way, right, some of the things tend to get distributed in certain ways. So that's a very nice kind of theory which governs these kind of things. But the interesting thing is now when we try to make an inference, right, we are looking at this distribution. And so this is the distribution of all possible values of the test statistic, right? And then I'm superimposing what I observed on it, right? And then the percentage of values of the test statistic which are above this is 0.62, right? So what is your conclusion from this? Is there a strong evidence against the null hypothesis, or we don't have a strong enough evidence against the null hypothesis? Anyone? we don't have a strong evidence, right? So a strong evidence would mean this value is unusual in the sense it would have fallen on this tail, right? So it would have given you a very small p-value, right? So that would have been a strong evidence against the. So now you see this is such a very kind of easy thing to do where you really don't have to remember any statistical distributional theory, no formulas, no distributions. What you just do is permute, right, the data depending on how you actually generated it, right? And then that would lead you to kind of making valid inferences by kind of just finding out the distribution under that randomization, right? So this is something which is very intuitive, right? And this is one of the basic frameworks which is kind of the foundation of this idea of analysis of randomized experiments. And we'll see kind of how this can be kind of generalized, right? So one of the things which we really did here was we assigned these 2 treatments to these 11 units in a randomized manner. So that was the key, because if we did not do that, we couldn't have been able to do this analysis, right? Because this entire idea of generating this distribution was based on that randomization, right? It was generated by obtaining those W's in exactly the same way I had done it to obtain my original data, right? So let's look at this role of randomization a little more carefully. What is it actually doing, right? So why did I choose to randomize, right? So I'm trying to figure out like which plots receive A and which receive B, right? That's what I'm trying to achieve through randomization, right? And this was my observed assignment, right? Where I got my test statistic as 1.83. But I could have observed another sequence instead, right? And I could have observed any of the 462 assignments with equal probability, the way in which I did it, right? So when I'm looking at these 462 possible assignments and I'm looking at these 462 possible sequences and I'm looking at these difference of means, right? So if I actually took the average of all of these possible values, what do you think I would have got here? Any idea? So if I computed this over all possible randomizations and took the average of these, right, what would appear here?
Yes. 0.
Sorry?
Yes. 0.
Would it be 0? So basically, I'll tell you the answer. So you can actually prove that what you would have found here is basically the true difference of the averages of the quantity which you are trying to estimate, right? That is the difference of the averages of those potential outcomes under the treatment and the control. That was what you are trying to estimate, right? So basically, so what this means is this, what we are actually estimating is an unbiased estimator of what you are actually trying to estimate, right? So on average, it is giving you the right answer, right? But only on average. Okay? So why is randomization good? It is protecting you from bad things. And what are bad things? Like, for example, this may not be a very good strategy because if you are assigning 5 of these, right, to A and 6 of these to B, that's probably not a very wise thing to do, right? Because you would then argue, just in the way we said that these 2 groups, right, are very different when it came to taking aspirin, one with these young ladies and one with these old people. It's quite possible that the fertility of the land increases from this direction to this direction, right? So whenever we are observing an effect of fertilizer B, that is likely to be the effect of fertility of the land and not the effect of the fertilizer, right? So we want to avoid that. That's one of the reasons why we do it, right? And that's being fair, and that's what is called unbiasedness, right? So, but this unbiasedness is only on average, because if I'm thinking about all possible repetitions of this, and I average over all possible repetitions, then I get fairness, right? But in reality, you are going to do it only once, right? So suppose you do it, right? And this is sometimes what happens. So you randomize. You find out, you pick one sequence, right? And then you come up with this. What will you do, right? So it's exactly like when you are thinking about doing this aspirin experiment, and then when you randomize, and you see that eventually most of the people under the treatment group are males and most of the people under the control group are females, right? It happened like that. But you did the right procedure because you randomized. What would you do, right? So in many situations, what people do is they would just cheat, right? They would just pretend, they not tell people like they randomized and got this answer. They would do it again, right? And sometimes try to figure out like, well, this is not the right sequence. Let us try to repeat this as long as we get maybe an equal distribution of males and females or an equal distribution of A's and B's, right, along this grid, right? So that's something which is a concern, right? So this is a challenge of modern day experimentation where these things are getting more and more complicated because we have a lot of variables associated with each of these plots, right? If you think of these as patients, right, they will have so many covariates associated with each of them, right? So how do we kind of protect against such kind of things? Okay, so let's see what we could do. So one possible strategy which we could adapt here is the so-called strategy of blocking, right, which is a strategy to protect assignments from bad randomizations. And by bad randomizations, I mean I don't want that kind of sequences of A's and B's, right? So what I could do is I could divide this into 2 blocks before I did the assignment. And in block 1, I assigned 3 A's and 3 B's, right? In block 2, I assigned 2 A's and 3 B's. That's one possibility, right? Then I can safeguard my assignment against that kind of bad patterns where the first 6 will be B's and the last 5 will be A's, right? So this is what Fisher said way back in the 1950s. He said, block what you can, randomize what you cannot, right? So to give that fairness on an average, try to block, right, the effects of these things which you know, right? And then whatever you cannot, randomize so that it's fair on an average, okay? So if we did this blocking, how should our analysis have changed, right? So remember how we analyze the data, right? So we were just calculating. So we did something like we had 11 of these plots, right? Now we have 6 here and 5 here. And we were looking at these 11 plots, right? And I have 6 data points under B, 5 from A. And I calculated the average difference, right? So that would have remained the same anyway, right? And what would have changed now is the way in which I would have generated that distribution, right? So that I would have generated the distribution exactly the same in exactly the same way as I did before, right? But following this guideline, right? So every time I would generate that distribution following this guideline, right, of blocking or dividing it into 2 groups and assigning 3 A's and 3 B's and 2 A's and 3 B's. That's how my analysis would change, right? So that was Fisher's second principle, right? Now, how do I take care of bad randomizations? So let's look into another example, which is very similar, but would really tell us about how this analysis exactly could be modified. So this is a diet experiment, right? So we have 20 animals, and we are trying to test whether kind of introducing an improved diet A versus a standard diet would really kind of help these animals in terms of certain characteristics, right? So, but these 20 animals are very different with respect to their age, sex, and different characteristics. So what I could do is I could block, right? Maybe I could create 2 blocks of 20 animals into 2 groups of 10 each, and then I could have applied this A versus B at random within each of these groups, right? The other possibility is this is called a matched pair experiment, which is an extreme case of blocking, where what I do is I try to create 10 pairs, right, taking 1 from each of these 20 animals so that they are as identical as possible, right? So each animal within each pair now gets either diet A or B, okay, and the allocation is decided by the flip of a coin, right? So what I'm doing is, see, I'm blocking what I can, and I'm randomizing what I cannot, right? So I'm creating these matched pairs, right? So every pair is a block, right? And I'm trying to make them as similar as possible, and then I'm deciding who gets what by the flip of a coin, right? That's what my randomization is about, okay? So I have 10 blocks now, and if I'm thinking about the potential outcomes, right? So I have these 10 pairs, and within each pair, I have 2 diets, right? And potential outcome for animal 1 and potential outcome for animal 2, I have 2 possible diets. So 2 potential outcomes here, 2 here. right? And the same happens for each of these 10 pairs or 10 blocks, right? So I observe one of these two, right? So if I toss a coin and I decide whether this animal gets this, and that means the other one of this group should get the other one, right? Should get B. That's how the assignment is going to be done, right? So this is the kind of data which you are going to generate from this. So you have the blue ones are diet A. So if this animal in pair 1 received diet A, right, animal 2 should get diet B, right? And that's how this is distributed. So immediately you see that this randomization or this data generating mechanism created a bunch of observed outcomes and some missing outcomes, right? So what should be a reasonable test statistic here? What should be a reasonable test statistic here? So I could actually look at the differences within each pair, right? That's probably a good idea to do, because in that way I'm trying to remove the effect of that particular kind of all variables which led to choice of this group in the first place, right? So I'm just looking at the difference of red minus blue for each of these blocks. That's giving me what is the difference for this identical pair, and I generate this difference, right? So how am I going to calculate a test statistic now? So I could actually calculate the average of these and take the absolute difference. That's a reasonable measure, right? How do I now test the hypothesis with this measure? The same idea, right? The first step, fill in all missing potential outcomes under the sharp null. What's my sharp null? The diets don't create a difference. So everything is filled in, right? I get my table. What do I do next? So I generate repeated values of the test statistic by drawing, right, observations from this exactly the way it was generated, right? So what that means is, for this pair, I flip a coin, and one gets A and the other gets B. Similarly, I generate data, I calculate the test statistic, and I do this thing, right? So this is again that distribution of that test statistic under all possible randomizations, and this is what I observed, right? So here I see that unlike the previous case, this is closer, right, to the tail, right? So clearly there is some evidence that this is not very usual in the sense that it is not in the middle part of this distribution. So there is some evidence that there is probably some difference amongst the diets, right? So this is basically the mechanism. So in 1925, Fisher came up with 3 fundamental principles of experimentation, and he called them randomization, which we already have discussed now, replication, that means you repeat the basic experiments by taking more and more units, right, which is also something very intuitive, and the third one was blocking, right, that is you block against things which you know, right, and then randomize against which you cannot safeguard, right. So, but now experiments are changing in various ways, right. So, for example, when I'm thinking about patients in clinical trials, the doctors will have thousands of measurements on each patient, right. So blocking is no longer intuitive at all. In many experiments, I have multiple treatment factors, right. So as I was mentioning in the stem cell lab, I have to deal with, so here I'm talking about one treatment and control, but there I have to deal with something like 30 treatments and controls being varied simultaneously, right. So that means what I'm looking at is not only the effect of one factor, but I'm looking at effects of 30 factors. There are 2-factor interactions, there are 3-factor interactions, there are 4-factor interactions, there are 30-factor interactions, right? So just think of the amount of variable selection which I have to do here, right? And then I have complex randomization restrictions, because these ideas are now being used in social sciences, and you try to impose a treatment on a school, right? You say that identify a school, and the school is randomly selected to receive a bonus for the teachers. They decline, right? So experimental units refuse to accept treatments which are given to them, but sometimes they do, and then later on they change, right? A patient is assigned medicine, and then eventually he doesn't take it, right? So there is a lot of missingness. There are complex randomization structures. So these are some of the artifacts of modern experimentation. But these principles are still very much valid, and I'm going to give you a few quick examples as to how we can adapt many of these principles under the modern kind of experimental scenarios. So one of the issues is, of course, this situation where we have a lot of covariates, right? Covariates means the variables which are associated with the experimental units and are measured, right? So it is, and the more the number of covariates, right, it is more likely that at least one of them will be imbalanced across the covariate groups, and blocking is not intuitive at all, right? So one of the solutions which actually came up from our department and Professor Rubin and one of his students, Carrie Lock-Morgan, who's now at Penn State, they came up with this very brilliant and innovative idea of what is called re-randomization. So this is a sort of formalizing that cheating idea. So if I get a bad randomization, right, I'm allowed to redo it, provided I do something before I kind of make a decision about that re-randomization, right? So that's basically a very innovative idea. Let's see what that means, right? So what that means is I want to define a measure. I want to make my re-randomization valid. I want to define a measure, right, which would tell me how balanced, right, the treatment and the control groups are, right? So if that measure is very small, that randomization is acceptable. If that measure is large, the randomization is not acceptable, and I would allow to redo it. But this is something which I have to decide before I did the experiment and I generated the data. Otherwise, it's not going to be valid, right? So just to give you an example with that fertilizer experiment. So what could be a measure of balance, right? So what could tell me whether this randomization is a good randomization or not? Any ideas? Any suggestions? Like if I'm just looking at this and I want to calculate a measure, right, which would tell me whether this should be acceptable or not, right? So any suggestions as to what could be a valid measure? So for, yes?
We can look at the length of the largest sequence.
Great, yes, fantastic. So you see, there can be a lot of possibilities. The length of the largest sequence is one, right? Because you want things to flip around as much as possible. You could look at the number of runs, right? You could also, one very intuitive measure could be just look at the positions where these letters appear, right? And take the averages of those positions and take the difference, right? So for example, B appears in 3, 4, 6, 7, 8, and 12, or 11, right? Just take that average and subtract it from the positions occupied by A. So there can be various measures, right? So that was a great idea. So 3 different randomizations, which is good and which is bad. Clearly, the third one isn't very good, right? So I want to find out a measure, and this measure could be something like what I just said. So we could actually take the averages of the positions occupied by these 2 letters and subtract. So this is pretty bad, clearly, because this is very large, right? These 2 are acceptable. So I could define a cutoff or a threshold. I could say that, well, anything less than 2 is acceptable, right? And this idea is also fantastic. Finding out the longest sequence is also a very valid measure. So then these 2 are acceptable and this is not, right? So what I would do is when I actually design my experiment, I would only accept randomizations which fall within that criterion, right? And I would not, which is something like this. How does that affect my analysis? Very minimally, right? Because when I generate the distribution of the test statistic, I would generate it exactly the way I would do it in the original experiment, right? So nothing really changes, right? So if you just think about how we did it earlier, so everything else remains the same, right? So I just define the acceptable criterion, and based on that, I generate the data, right? And then I analyze using the randomization test. I calculate the observed value of the test statistic exactly the same way. Assuming the hypothesis to be true, I impute the missing potential outcomes. Nothing changes here, but what changes is when I generate distribution of the test statistic, right, using repeated assignments, I always generate those repeated assignments under the same mechanism. That is, I don't consider those which are bad by my criterion, right? And I just generate, I accept randomizations that are acceptable. That's how I do it, right? And then everything else remains the same, right? So it's just a simple strategy. Why didn't people think of this before? Because they didn't have the computing power, right? Even 10, 15, 20 years ago, right, we couldn't do kind of this many randomizations in a fraction of a second, right, and generate these nice distributions the way in which we can do them now, right? So you have large number of factors, you have complex randomization, nothing matters, right? You should only be able to repeat your original algorithm, right? You should be able to write a code which generates that data, and you should be able to run it over and over again, right? That's what you need to do, right? So that's a kind of very nice way in which you can address this issue or protect your data generation from these kind of unacceptable randomizations which you really think are going to be bad, right? So how does this look like when you have more than one covariate? So in the previous example, we only had one covariate to guard against. That was the position, right? Suppose you have two, and these two are continuous covariates, right? So what I'm plotting here is, suppose I choose a randomization, right? And then this point is giving me the difference of one particular covariate, that's x1, right? The average in the treatment group minus the average in the control group, right? And the same thing for covariate 2 is being plotted here. So it's just a two-dimensional representation of covariate balance between the treatment and the control group, right? So I generate different randomizations and they look like this, right? I generate more randomization. So you would probably assume that this is not so good, right? So you would want everything which is close to 0, but how close? That's your choice, right? So, and how could you do that? You could do different ways. You could do it in different ways. You can choose a box, but that may not be a very good idea because you want to kind of maintain that kind of distribution which the covariates are having. And in this case, they have something like a symmetry, which we call an ellipsoidal symmetry, which is kind of a common thing for distributions like the normal distribution or the t distribution, right? So you might want to choose something which is like this, right? So you might want to choose something like a circle or an ellipse within that and reject the rest, right? So everything which falls within this would be sort of acceptable randomizations, and whatever is not within this is an unacceptable randomization, right? So easy to write a code. So all we need to do is to determine how we would define this ellipse, right? And there are different ways of doing that once again. One of the things which has recently been proposed is to use a distance which is called the Mahalanobis distance. Now this Mahalanobis is a complicated name, like my name, because we both hail from the same country, that's India. And P.C. Mahalanobis was actually the founder of the Indian Statistical Institute, also an institute from where I got my graduate degree in statistics. So Mahalanobis defined a distance which is basically a multivariate distance between two group mean vectors. The idea is simple. So you're just trying to calculate how different two groups are by kind of taking a one-dimensional transformation of these two vectors, right? Adjusting them by the variance covariance matrix of the groups. So that's basically the Mahalanobis distance. And it has some nice properties. So there are some interesting mathematical things which can be done, but implementation is very easy. So all we have to do is to decide upon an acceptance criteria. So basically it's telling me how large that circle is going to be, right? Whether I'm going to accept a circle which is very large or a very small circle, right? And clearly there is a trade-off here. So if my circle is very small, then basically that means I'm throwing away a lot of randomizations and I don't deem them to be appropriate, right? On the other hand, if I'm having a large circle, that means I'm accepting more. Now, there can be a computational trade-off here, right? But once again, I mean, this obviously is going to be one concern as you have higher and higher dimension of covariates and the way in which you throw these off. So there can be some empirical studies which can be done on this, and some have been done, right? But this is something which is a very kind of nascent area in research, and people are trying to find out what could be the best ways of doing this. So effectively, what is being done is if I'm looking at the distribution of the treatment average and covariate average, control average of this covariate X, then if I did not randomize, it would have a distribution like this, right? But now I'm shrinking this distribution by disallowing certain randomizations based on my criterion. And I'm shrinking this. So now my groups are much more comparable, right? That's basically the idea. So this strategy has been applied to quite a few experiments in recent times. So for example, this was a medical experiment. This is just a demonstration with a few covariates. So what this shows is basically the realization of what I just now showed for one covariate for several covariates. So the blue lines basically represent the distributions of these covariates if you would do an ordinary randomizations without throwing away anything. And these red ones represent the distributions under this re-randomizations or restricted randomizations, right? So these bands actually show how much you are able to shrink that distribution by restricting the randomization, right? And what is most interesting and innovative about this is you really don't have to think a bit about how you're going to adjust this analysis, right? Because if you write a code for doing your randomization test, extending that code to the re-randomization test is absolutely trivial, right? Okay, so this is an example. Now here is another example. Here there are a bunch of covariates. One of the things which you could also do is, it's not that all covariates are equally important, right? So some covariates, like when you are doing a clinical trial, doctors will tell you that some covariates are more important as compared to the others, right? So you want to give more protection against those covariates. You want to make sure that those are better balanced as compared to some covariates which are less important, right? Then probably you might also want to see that in not only the means of the covariates in the two groups, but also the quadratic terms, right, are balanced, right? Or higher order moments, right, are also balanced. So you could add more and more terms. So you could actually have different acceptance criterion for different groups of covariates, right? So you could call these tiers of covariates. So first tier, which is the most important tier, and that has to be controlled very, very strongly, right? Then you have a second tier, which probably you can afford to control a little less stringently. And as you see, like for example, I think this probably is a group which was controlled not as strongly as where these two covariates, right? So you really want to. So this is again a trade-off between computational cost. Ideally, I would like to control everything well, but I can't do that, right? Because it's going to be very, very expensive computationally. So I just have to make a choice. And there is a lot of domain knowledge which should go into these choices. So that's the reason why experimenters and data scientists should really sit with people having domain knowledge and trying to figure out what should be the best strategy, okay? So this is how re-randomization would work. Now let's briefly talk about these multi-factor experiments. So this is something which we had been involved in a few years ago. So the Department of Education in New York were trying to come up with some new initiatives to improve the performances of these schools, and they would measure the performance using something like a cumulative score on the annual progress report. And they had 5 new interventions, like whether they would introduce a bonus scheme for the teachers or not, right? Whether at the middle of the year they would do a quality audit or not, or a quality review or not. So that could be called A, this bonus scheme could be called B, and similarly you have 5 factors labeled A to E. So basically, when you have 5 factors, right, so each has a treatment level and a control level. Treatment level is if you get it, control level is if you don't, right? So you have 2 to the power 5, 32 combinations here, right? And so what that means is if you have 224 schools, then you have to distribute these 224 schools into these 32 treatment combinations, right? How would you like to do that? You would do that randomly, so that every treatment combination is assigned to 8 schools, right? However, you actually have a problem because there are many covariates there, and there are about 50 covariates associated with each school. And these include like different kinds of things, starting from attendance rate of teachers, ethnicity of students, different categories under ethnicity, the location, geographical location, income, a lot of demographic information, right? So when you do this assignment, you have to be careful, like whether you are really kind of balancing these assignments over these 32 groups, right? But that's not a very easy task because your choices are not a lot, because you only have 224 and you have 50 covariates to balance, right? So, but then we could think about different tiers, right? So what are we trying to find out here? So first of all, we are trying to find out the so-called main effects of each of these factors, right? So that's the marginal effects. If everything else remained constant, what happens if you give a bonus versus not giving a bonus? That's the main effect, right? Then you might be interested in 2-factor interactions. That means what happens if you keep 3 factors fixed, right? And then what is the effect of changing the level from giving a bonus to not giving a bonus if the level of this quality review changes from 0 to 1. That is, it's given or not given, right? So that's a two-factor interaction. So an interaction means how does the effect of one factor on the response change under changes of the other factors. That's what an interaction means. And that's how you define 2, 3, 4, 5-factor interactions, right? Now, typically, you would imagine that the marginal effects or the main effects are probably the most important, right? So I might want to protect them the most. And then my secondary concern probably would be to protect the 2-factor interactions, and then the 3-factor interactions, right? So I can design my re-randomization strategy based on this kind of an idea that I would like to protect my main effects most, followed by kind of 2-factor, 3-factor, and 4-factor interactions. So this is something which we have been contemplating. So a completely randomized assignment is okay, right? But once again, it only balances on an average, right? So we need to balance over 50 covariates. So we are giving maximum protection to the 5 main effects, right? We are giving a little less protection to 2-factor interactions, and we are giving, let's say, 0 protection to 3, 4, or 5-level interactions, because this is, again, related to domain knowledge. You might talk to the school authorities and ask them, like the DOE authorities, and ask them, does a 3-factor interaction make any sense, or is it important? They might say it's not really very important, and you can drop that, right? So this is what we obtained from this experiment. So we did a re-randomization where, let me tell you what these figures are. So this is how much percentage reduction was achieved in each of these covariates, right? The difference of the treatment means, that is at x1, xt bar minus xc bar, after doing a re-randomization. So, so this is, so for example, the red points refer to the main effects, and these are the different covariates. So as you can see, most of these, in most of these cases, we were able to improve the balance to about 40% of the original assignment through this re-randomization method. Okay? When for the 2-factor interactions, we were able to improve, we were able to shrink this distribution about 20% more than what was achieved without doing this re-randomization. And for 3-way interactions, we didn't achieve balance because we did not choose to protect them, right? So we just left them unprotected, okay? So probably you could think about a better visualization of this. And so not the greatest of visualizations, but there are, yeah, I mean, this is an interesting thing. How could you make this presentation better in terms of different covariates? So, okay. So what we have talked about is randomization. Why randomization? And what happens if you do not do randomization? How can randomization be used to infer from the data, right? How do you analyze the data based on how you collect it, right? So, and how do you block it? How do you re-randomize your experiments? So in this kind of factorial experiment, we could do similar randomization tests. So we can generate distributions, right, for each of these main effects. So x1, x2, x3, x4, and x5 denote those distributions of the main effects. This denotes the interaction between 1 and 2. So you can quickly find out that this is probably something which appears to be significant, more significant as compared to the others. x5 seems to be very strongly significant. That's the main effect of factor 5. When I'm looking at these, is there an interaction which appears to be significant? Probably this one, right? The interaction between 3 and 4, right? So this is a quick visualization of kind of which of these effects, main effects and 2-factor interactions, are stronger than the others. And we are, of course, doing something called a multiple hypothesis testing here. So you might kind of want to protect your procedure from the bad effects of doing such simultaneous hypothesis tests, and there are methods for that, which I'm not going to go into. Okay? But how these randomization distributions were generated, they were generated exactly the same way as I demonstrated before, right? So just draw repeated kind of assignment vectors, right, from your assignment mechanism, exactly the way you did it, and obtain values of these test statistics and plot them and superimpose what you observed, okay? So I think if we have to modify Fisher in 2015, we would just modify it by adding a couple of words here, right? So block what you can. Fisher said randomize what you cannot. So we would just say re-randomize what you cannot. But do that in a very specific way, right? So this is something which actually can help you kind of do causal inference a lot better from multi-factor experiments where the experimental units have such a large number of covariates. And Fisher said analyze as you randomize. We are going to say analyze as you re-randomize. Okay? So far, what we have talked about, you must be wondering, like, at the beginning, I raised a question about the scope of inference, right? So when I formulate a question, right, whether an aspirin really improves your situation with respect to getting rid of a headache, whether I'm talking about this class or whether I'm talking about Harvard as a whole or which population I'm talking about. So the way in which this entire inference was conducted, it should be clear that the scope of my inference is restricted only to that finite population, because so far, when I talked about these potential outcomes, right, I assumed that they were fixed quantities, right? So when I'm talking about this y1 and y0 or yt and yc for a unit, I'm visualizing them to be fixed quantities. So what that means is the scope of my inference till this point of time is only restricted to the population of units I am studying, right? Now, is that a good idea? Probably not, right? So when I advertise my aspirin, right, I should be able to do it with respect to a larger population, right? So I definitely need to extend my analysis from a finite population of 224 schools to a larger population, right? Now, how can I do that? Okay. So this is something which eventually I would like to do. And also, so far, I have really kind of visualized my potential outcomes as being fixed quantities, right? But actually, they are not. When I'm thinking about what would happen if I took an aspirin, that's a random variable, right? That depends on many things. And I would like to make a statement or formulate my problem based on those possible situations, right? That would give me a better applicability of the results of my experiment, right? So how can I do that? So perhaps I want to extend this inference to a larger population, which I call a superpopulation. Now, the superpopulation may be something which is finite or well-defined. It could also be hypothetical, right, in terms of a statistical distribution or something like that, right? So right now, whatever inference I have done is based on this finite population. I have imputed these missing outcomes, right, and I've done this randomization test. But I have not really made any distributional assumption. I have not kind of talked about any statistical distributions or probability or stochastics, except for the fact that I have a probability distribution over the randomization, right? That's the only stochastic or probabilistic element in this entire analysis, right? But now I could bring in more, right? So for example, I was watching the video of your last class, and last week you probably introduced the Bayesian analysis. Is that right? So let's talk a little bit about how we could extend this to a superpopulation scenario, right? So I could put a model on this, right? So I could visualize this finite population to be a random sample from a superpopulation which satisfies a certain distributional characteristic, right? So for example, this I represents the ith unit amongst these 224 schools, and I can assume that this is drawn from a distribution, a normal distribution, let's say, with mean mu t and mu c with a certain variance covariance matrix, and then I put something called a prior distribution over these means because I don't know that, right? So basically, when I'm talking about a superpopulation, I'm visualizing this distribution to be true for this superpopulation, right? In a sense that these 224 units are sort of randomly sampled from this larger distribution, and I'm putting one more layer of probability structure, uncertainty structure on these mu's. I have no prior idea, so I would say that these mu's are also normal with means at zeros, and probably they have certain variances tau squared. These off-diagonal elements indicate the covariance between these terms. Now, probably this means I'm assuming they are independent. These tau squares I can put as large as I want, which are called dispersed priors. That means I have no idea about what they are, right? So that's basically my hierarchical model. Now, this mu t and mu c they are the parameters which will tell me about the causal effect in the superpopulation, right? So I might want to study the difference mu t minus mu minus mu c, when I'm trying to study the superpopulation effect, right? So this is called a Bayesian model. So what is happening here is really from this hypothetical model, you use your assignment mechanism W to generate this observed data for that finite population for the 224 schools, right? So that's what you observe. And then what we could do using these powerful computational techniques and Bayesian methods is we could use this entire information to obtain what we call the posterior distribution of these parameters mu's conditional on observed data and what randomization vector you obtain. Okay? So I believe Joe already has told you that conditioning is the soul of statistics, right? So you condition on what you observed, right? And based on that, you find out the uncertainty associated with these superpopulation parameters, right? And that helps you extend your inference from a finite to a superpopulation. Now, under this setup, should our finite population inference change? What I mean to say is, so far, we have just kind of imputed the missing potential outcomes by exactly the value which we have observed under the short null hypothesis, right? But could we do better now? Definitely. So through all these, we now could come up with a model which allows us to impute the missing potential outcomes from a distribution, right? So we are now doing that imputation by augmenting some stochastic element to that imputation, and that entirely is dependent on this uncertainty defined through the structure. So we are, instead of just imputing those missing outcomes the way we see the observed ones, we are going to impute them using a probability distribution which is conditional on what you observed and the randomization. So you notice that in this there is no mu t and mu c, right? So why is that so? Because when we are looking at this, we are integrating them out. That means when it comes to the finite population, we are just kind of visualizing the way in which we can predict these missing observations based on the observed data, right? For the finite population, these mu's don't have a role because we are just looking at the predictive distribution of these y's, right, given what we have observed, right? So what this essentially means is unlike the previous case where you would remember under the sharp null hypothesis, we were imputing these missing outcomes by exactly their observed counterparts. Now we are not going to do that, right? We are now going to draw them, generate them from a distribution of these missing outcomes given what we have observed, and that will encompass this entire set and this observed W. And that obviously will come with a degree of uncertainty because it's being drawn from a distribution. And then we are going to make our inferences, right? So this is basically an added layer of uncertainty which goes into this thing. So yeah, we are almost out of time. There is a lot of interesting things which can follow from here. So if you want to learn more, we have Stat 140 and Stat 240. Stat 140 will be offered in next fall. Stat 240 is almost on the verge of conclusion this semester. Yeah, I think there'll be a lot of additional things if you want to learn more or are interested. But I would like to thank Joe and Hans-Peter for giving me this opportunity. And please let me know if you have any questions.